So, rather than doing those set proofs to show two sets are equal, where you're showing each side is a subset of the other side, you can use these set equivalences that we talked about earlier in this section and do some rearranging. And sometimes that is a little bit easier than doing an entire proof. So let's look at this one. We want to show that A union B minus A intersect B is the same thing as A minus B union B minus A. And in fact, this is basically, and in fact not even basically, it is for sure A circle plus B, the symmetric difference. So let's show this using our set equivalences. My first thought is that I need to write things as A minus B and B minus A. So maybe what I'll do is I will use Law 11, the set difference simplification, to simplify this, and then move things around to get it looking like A minus B union B minus A. And I'll have to use the set difference simplification in the other direction to reintroduce those differences. So that's my plan. Let's go ahead and do this. So A union B minus A intersect B, that's equal to, well, the first set, A union B, intersected with the complement of the second set. So A intersect B complement, and that's by 11. Now, let's use De Morgan's law here to simplify this. Again, if I could get things in terms of A intersect the complement of B, union B intersect the complement of A, I'll be done because I can use 11 in the reverse direction. So again, that's my plan. So let's go ahead and let's use De Morgan's law for sets. So this is A union B intersect, and put some brackets here, the complement of A union the complement of B. And this is by 6. Now, let's use distributivity to distribute this out, since we have two sets with the unions joined by a set with an intersection. Maybe a good idea is to use distributivity. We'll have to use it twice. This is very similar to expanding two binomials, or FOIL. So we're going to expand this guy here with this, so that is A intersect B, or sorry, A union B intersect the complement of A union A union B intersect the complement of B. So that's the first bit of our FOIL. So that's that there. And that is this here. So I'm treating this thing like one set. You can think of this as the letter C. C intersect complement of A union complement of B. So it's going to be C intersect the complement of A union C intersect the complement of B. And this is by distributivity, and we're going to do it again. Let's use distributivity again. So now, using distributivity once more, we get A intersect its complement union B intersect A complement So that is, I'll do this in green. So that's that with this. And then in yellow, that with that. And we'll do the exact same thing with the other one. Union. Maybe I'll put this all in a big bracket just to help keep things straight. Let's do the same thing. We have A intersect B complement. That is that with that. And then union B intersect B complement. That is that. So that's using distributivity twice. And that is 4. Okay, so we did 4 again. And now we notice some things. We like when we have sets together with their complements or sets together with themselves, whether it's union or intersections, because you can simplify them to either the empty set or the universal set or itself. So in this case, we have A intersect its complement. What elements are in a set and its complement? None of them. So this simplifies to the empty set, union B intersect the complement of A. This looks good so far. Put some brackets around that. Union, let's do the same thing over here. A intersect B complement. Union, and again, we have B intersect its complement, and obviously nothing is in itself and its complement. So that's just the empty set as well. And really, we just applied number 9 here. So if you have a set intersect its complement, it's the empty set. Okay? And now let's have, before we continue, let's have a look and see if this is going the way we want. And this looks pretty good. I'm looking at this B intersect the complement of A, and that by 11 I can say is B minus A. This A intersect the complement of B is A minus B. So these things are showing up here. This is looking good. All right. We have a set unioned with an empty set. And of course, if you union with nothing, then you just get what you started with. And that's rule 8, that we can just ignore that empty set. It's adding nothing to the set. And we're taking the union. So this just becomes B intersect the complement of A, union A intersect the complement of B, and that's by 8. The union with the empty set is just the set you start with. Okay? And again, well, we're almost done here. We know by 11, this is another way of writing A minus B and B minus A. So B intersect the complement of A is B minus A union. This is A minus B. That's by 11. And we're almost done. We're not quite done. It asks us to put it in this order. So let's go ahead and put it in that order. We'll just use the idea of commutativity. We have 2 sets with a union between them. Order doesn't matter. So this is A minus B union B minus A. And that's by commutativity, which is number 2 in our sheet. And that's it. We started with A union B minus A intersect B. We did a little bit of set equivalence operations. In fact, the only tricky bit, I guess, was figuring out how to use distributivity. Here, everything else looked pretty straightforward. We used the idea of equivalence of set minus first, and then we noticed we had a complement of an intersection of sets. So we used De Morgan's law for sets here. And then distributivity made things really nice for us. We were able to make these be the empty set, and then they went away, and we just, in some sense, followed our nose until we ended up with what we wanted. Let's look at one more example. And let's scroll down to see this. And this is a good opportunity for you guys to try it. So start with one side. Doesn't matter which side you start with. And see if you can get it looking like the other side using our rules. So give it a go. Pause the video now and try it yourself. Okay, let's get going here. So again, it doesn't matter what side you start on. I'm looking at this, and I'm thinking it might be easier to start on the left-hand side and simplify it to the right-hand side, since the right-hand side is a little smaller than maybe using some of these things like either idempotents or unions or intersections with empty sets or universal sets. Things like that might make things a little bit smaller. So that's my idea anyway. So let's start on the left-hand side, a minus b intersect a minus c. And maybe even before that, let's explore what that looks like with a Venn diagram. It's always a good idea to kind of get a feel for what these sets are when you're doing these things. So here is, let me shade this in blue. A minus b, that is this bit here. This is your a minus b. Okay, and we want to intersect that with a minus c, which I will do in green, and the overlapping colors is going to be the region that we want. So a minus c is this bit. Again, I'm just pretending that b isn't even there because I'm just interested in a minus c, so that's in green. And since we're interested in the intersection, it's where both of these match up. So it is indeed, maybe I'll do this with an actual pen, it's indeed this area, the intersection, the stuff that is in both sets. So a minus b was your blue, a minus c was your green, and the whole thing was in red. So that's what that set looks like. Okay, let's look at a minus b union c. So we'll do this again. Again, this isn't a proof. This is just to get a feel for what's going on. Here's a, b, and c. So we need to figure out what b union c is. I'll do that in blue. So that is everything that's in B or C. So it's all of this. There is the union of B and C. And I want A minus that. So I'll do that in green. So A minus that is going to be this region here. And I'll highlight the region that we want. Again, it's exactly the same. So this looks good. It looks like this is a true result from our Venn diagram. Now we just have to prove it mathematically. Okay. So let's use 11 again to get rid of those set differences. So this becomes A intersect the complement of B intersect A intersect the complement of C. Okay, and that's by 11. And remember the form of what we're trying to get in. We're trying to get in A minus B union C. So let's keep going. We want to get B union C somewhere. Notice that here we have only intersections. So we can apply commutativity and associativity to move things around however we want, because these are all the same connector. They're all intersections. Think of it like multiplication. If you have a bunch of things multiplied together, you can move it around however you like. So I'm going to move the A's together and then move the B and C's together. So I'm going to make this A intersect, oh, wrong color, intersect A, intersect B complement, intersect C complement. So that's 2. That's me using commutativity to arrange these in whatever order I like. And I'm going to group these things. I'm going to use associativity to group them however I like. And remember, that is because the only symbol between them is intersect. They all have to have the same symbol. Otherwise, you have to use distributivity. Okay, so this is looking good, and the reason I did that is because now we have this B complement intersect C complement that's starting to look a lot like B union C. You can think, well, maybe De Morgan's law will apply here, and I can get a B union C. And A intersect itself by idempotence. A set intersecting itself is just that set, so we'll do that. A intersect the complement of B intersect the complement of C. By idempotence, I can do that. Now let's use De Morgan's law here. So we'll have A intersect, well, we'll take the complement of a complement. So we'll take B complement complement, so that is just B. And the intersect switches to a union. The complement of C is C. And we take the complement of that entire set, and that is by De Morgan's law 6. Morgan's law for sets. And then, hey, look, I have A intersect some complement of a set, so I can write this in terms of a set minus. So it's A minus that set, B union C, and that's by 11. So again, it's a good idea to keep in mind where you want to go. I always wanted to have this A minus B union C. And if you don't see the steps initially, sometimes it's good when you're figuring it out to start from both sides and work towards the middle. So let's say you just do a couple of steps here. Maybe you just did one. You used your idea of the set minus equivalence to simplify here. And you're like, I can't really see where this is going. Well, in that case, maybe starting from the bottom and working up would be a good idea. So start with your A minus B union C. See if you can simplify that. You use 11 to get here. And then from here, you can use De Morgan's law to get somewhere here. And so then you're thinking, how can I get from this step to this step? And then you have a little bit less of a jump to see where to go. So sometimes it's good to do that. But when you're writing it up, remember, you have to write it up starting with one side and going to the other. So just make sure when you're writing it up, it's all in a logical order that follows. So again, this is a lot like logical equivalences, except you're dealing with sets. Sets and logic are extremely related, so it's unsurprising that these ideas are very similar.